And for the next week of Chapter 7, this is the most important fact. Can you work with fractions? In grades 7 and 8, you were introduced to fractions. And you did fractions with numbers. In grade 9 and 10, you continued working with fractions with numbers, but it started also to work with fractions with algebra in grades 10 and 11. In grade 12, we not only have to do fractions with algebra, we're going to do fractions with trig functions, and we have to be really, really good at the basic rules for fractions. You have to know how to add fractions, subtract fractions, multiply fractions, divide fractions. And overall, this is going to be very important. We need to use those rules to get something to be a single fraction. So we're going to do the following 1, 2, we'll do them in this order and we'll do them together to review our rules, but now we're reviewing our rules with just variables. There's no numbers involved. So we have to know our rules really well when we're dealing with something abstract like variables. Sometimes you can do a rule when it's numbers, but then can you still do the rule if you take away numbers and put variables there instead? So for number 1, we need a single fraction, and we currently are adding 2 fractions. So we have to go to our rule. What is the rule for adding fractions? You can only add fractions if you have a common denominator. The denominators here are b and c. They're not the same. So how do we make a common denominator? Well, this one, if it had a c, and if this one had a b, then my denominators would both be like this, bc. But in order to add a b on the bottom, or a c on the bottom, you'd also have to multiply the top. And so if I multiply the top and the bottom to get my denominators the same, now, if your denominators are the same, how do you add fractions? Well, you just have to add the tops. And this is a single fraction where what we started with was 2 fractions. So this is the skill that we need to be able to do. We need to be able to write something as a single fraction, and if you're adding or subtracting fractions, you need a common denominator. Right? How did this question show up in grade 7 and 8? You had numbers, right? And then you would have gone, oh, my common denominator is 6, so I need to multiply this by 3 and this by 3, this by 2 and this by 2. You would have got 3 over 6 plus 2 over 6. And then you would have been able to say 3 plus 2 is 5 and get 5 over 6. We need the common denominator before we can add the tops. And when we multiply to get the common denominator, what we're doing is we changed 1/2 to 3/6. And with numbers, you can see they're the same thing, just written with different numbers. It's the same thing we did in algebra. AC over BC is the same as A over B, just written with some more variables. Once that denominator is the same, then you can add the tops. Number 2, we have AD over CD. So we have to remember our rule for dividing fractions. If you have a fraction divided by a fraction, our fraction rule is multiply by the reciprocal. So the second, or the fraction that's on the bottom, you write the flip of it. So instead of C over D, I write D over C. Now I'm multiplying 2 fractions, and the rules for multiplying fractions, you can multiply your numerators and multiply your denominators. So now I have a single fraction whereas I started off with a fraction divided by a fraction. Number 3. Number 3 is the only one that has started as a single fraction. A squared minus AB over B squared minus A squared. But sometimes a fraction's not in simplest form because it can be reduced. For example, if I told you numbers, 8 over 24, you'd be like, oh, both of them can divide by 8, so this reduces to 1/3. That would be the simplified form. How do we do that same thing when we're dealing in variables? Well, dealing in variables, what we would do is we would try to factor. If we can factor, and if a factor is identical, then we can simplify. In our numerator, can you see that you have a common factor of A that you can pull out? And in our denominator, we have a difference of squares. So that can be factored as B plus A, B minus A. And the only way you can cancel out factors is if they are identical. At this moment, nothing is identical, but something is close. Can you see that you have an A minus B, and that's really close to B minus A, but not quite? So a special note that you probably wrote down in grade 10 and grade 11, and you're going to write it again now in grade 12, that B minus A is equal to negative. If you factor out a negative, that would change the A to positive and the B to negative. So you could factor out a negative, and then it switches the order. So that would allow me to rewrite this A over A times A minus B over, factored out a negative, I still have the B plus A, but now I have A minus B. Now these are identical, and they can simplify, leaving me with negative A over B plus A. Where you put, if you have a negative in a fraction, and that negative is in the denominator, you can move that negative to the numerator, or you can put that negative in front of the fraction. You can choose where you want to put that negative. But this is simplified version of what we had originally. So if you have something that's already a single fraction, and you can factor it, you will want to factor it to see if something is simplified. Okay? And finally, and this is what's going to probably occur the most often in this unit, is fractions inside fractions with adding and subtracting. A over C plus 1 over B, B plus C over A. And our strategy will be to get a single fraction in both the numerator and denominator, and then we'll divide. So right now, we have lots of fractions inside of fractions. And by numerator, here's the main fraction line. Do I have a single fraction in my numerator? No. Denominator, do I have a single fraction in my denominator? No, this is B over 1. That's not a single fraction. So our strategy will be, can we get a single fraction in our numerator? Can we get a single fraction in our denominator? And then if we have a fraction over a fraction, we have a rule for dividing. So to start off with, in my numerator, if I want a common denominator, this one needs to be multiplied by B and B, this one by C and C. In my denominator, to get a common denominator, This one's going to need to be multiplied by a and a. What do I get? Here's my main fraction line. Can you see in my numerator, I would get a common denominator of BC. If I added the tops, I would get AB plus C. In my denominator, I'd have a common denominator of A. If I added the tops, I would get AB plus C. You're going to have so many fractions written. Sometimes, like, I wrote my main fraction line bigger and darker to help me visualize what's on the top, what's on the bottom. And now that you have a single fraction in your numerator and a single fraction in your denominator, you can use your rules for dividing. What's the rule for a fraction divided by a fraction? Multiply by the reciprocal. So this is going to equal, the top one's going to stay the same, multiplied, and the bottom one is going to be the reciprocal. At this moment, we could multiply the tops and multiply the bottoms, but if you are multiplying and factors are identical, which they are, this will simplify with this. And this whole thing simplifies to A over BC. Okay? For this unit, we're going to be doing this the same, but instead of letters A, B, C, and D, we're going to use sine theta, cos theta, tan theta, cosecant theta, and all of those. You're going to really have to know these fraction rules. And this strategy of getting a single fraction, and especially when you have fractions inside of fractions, getting a single fraction in your numerator, getting a single fraction in your denominator. If you know your fraction rules, this unit is going to be just fine. If your fraction rules are even a tiny bit needing practice, this will be hard and you will have to practice a lot. So you need to get your fraction rules really, really strong. Okay, so what does this look like for us? You can turn the page 606, and we are going to get introduced to something called a trig identity. So if you want to take out your highlighter, and highlight the definition of what a trig identity is. It is like an equation that's always true. And then in the box, they list some that you already know. You already know that cosecant, its definition, is 1 over sine. That's always true. So since it's always true, it's called an identity. You already know secant is 1 over cos, and cotangent is 1 over tan. Beside these ones, I would like you to also write that you can flip them this way. That sine theta is 1 over cosecant theta, that cos of theta is 1 over secant theta, and that tan of theta is 1 over cotangent of theta. If one is a reciprocal of the other, then you can write it both ways. We also learned that tan of theta was sine theta over cos theta, and cotangent theta is cos theta over sine theta. And the other identity, if you want to write it here, we're going to look at it more in depth a little bit later, but we'll use it as well. This is always true. This was one of our big ideas from chapter 6. that sine squared theta plus cos squared theta is equal to 1. That's always true, so we can use that as well. Okay. All right, so what we're going to do is we're going to be introduced to something called a proof of a trig identity. And I've got a handout for you. We're going to do learn a technique of what it means to prove something. So it starts with question number 5. And question number 5, and you are going to need loose leaf for this. Does anybody not have loose leaf? Because I have extra. Anybody else need anything? So question number 5 says prove that cos of t secant of t equals 1. So there are some rules for proofs. And we do certain things to make sure that we follow the rules. In a proof, you want to show that something is true, but you can never use it and assume it's true before you prove it's true. So the way that we do that is where the equal sign is, we will always draw a straight line to tell us we're never allowed to move something from one side of the equation to the other. Because you're only allowed to move things from one side of the equation to the other if they are equal. And you've been asked to prove that they're equal. So what you can do, though, is you can manipulate things on the left side, and you can manipulate things on the right side, and it's a puzzle to see if you can manipulate things so that both sides are identical. And what we are going to be allowed to do, and the only tools that we have are on this box right now, on the left. If you see a cosecant, you are allowed to change it to 1 over sine. If you see a secant, you're allowed to change it to 1 over cos. If you see a cotangent, you have a choice. You could change it to 1 over tan, or you could change it to cos over sine. So you are allowed to use these things to manipulate. What does that look like? Well, I look at this equation, I have a cos and I have a secant, and I have a 1. I could choose something to change. Generally, you're going to find that since you're more familiar with cos, you're more used to that, if you have a secant, you'll change the secant to something. Now, you're not going to want to flip back and forth between this list. So you'll want to make sure that you know these and have them memorized. And we should already from chapter 6 know that secant is the reciprocal of cos. So instead of writing secant, I'm going to write 1 over cos. And now our fraction rules come in. This is cos over 1, and I'm multiplying by 1 over cos. How do you multiply fractions? You multiply the tops, you multiply the bottoms. Also, when multiplying fractions, if 2 factors are identical, they will simplify. So we could simplify this at this point. Cos divided by cos, that'll be 1. Then what am I left with? 1 times 1, which is equal to 1. And this proof right here is so easy that you will never get one this easy. Just one step and done. But it's to show us how do we go about the formatting of a proof. So first, we drew the line to separate the sides. Then we manipulate until the two sides are identical. And finally, we write a statement saying we noticed that we made them identical, and we can say the left side equals the right side. So in mathematics, writing 3 dots means therefore the left side is equal to the right side. And often in mathematics, proofs end with QED, which is a Latin abbreviation. So you probably don't know what it stands for. Quod erat demonstratum. I don't know who decided that they wanted to use Latin at the end of a proof, but it's kind of cool and it's kind of historic. So we write the left side equals the right side, QED to say that we finished. Because quod erat demonstratum basically says what you asked me to show has been demonstrated. So.
Hi there.
Hello.
Hi, can I have Addison to the office for a moment?
Yeah.
Thank you.
And then, you don't have to do this, but I draw a little box with a little shading. That's my little symbol when I'm done a proof. It's something I did for all my university math proofs. You can like a happy face, or you want to draw something. Sometimes proofs are difficult, and having a little symbol at the end just makes you feel like, oh, got it. So, I add a little box at the end. Okay. So, this is a proof. We write it out again. Where the equal sign is, we draw a line. We manipulate until both sides are identical. And then, we write a statement saying that we noticed that we got them done. We are eventually going to do this whole sheet. They start off easy and get very difficult. We have to develop more strategies as we go along. But we're going to do a couple more together. So that was, right, the first couple. If we get up to, 5, 6, and 7, very basic. You'll be able to do those on your own. Let's do number 9 together. So we want to prove, so we rewrite the whole question out. Cos y times cosecant y equals, and on the other side we have cotangent. And this is a good one to do because it will introduce you to your first major strategy in proofs. Okay? Again, we already have talked about fractions. Getting things as a single fraction will be a major strategy. But when you have something like this, and you have to make a decision to change something into something else, it can be difficult to say, well, what should I change? I could change the cos. I could change the cosecant. I could change the cotangent. What happens if I change the wrong one and I don't get to the solution that I want? So one of the strategies that becomes very important, and if we look at our list that we have here, notice that every single trig function could be changed to either sine or cosine. If you have cosecant, it can be changed to sine. If you have secant, it can be changed to cos. If you have cotangent, it can be changed to tan, but it could also be changed to cos over sine. Tangent can be changed to sine over cos. So as far as a strategy goes, if you have an option, you might want to change everything to sine and cos and see what happens. So if you're unsure what to do, like on this one, you might go, I don't know what to do. Can you change everything to sine and cos? I'll try that. So cos, I would keep the same. I'm not going to change that one because that one's already cos. Cosecant, I'm going to change that one to 1 over sine. And cotangent on the right-hand side, I'm going to change that one to cos over sine. And just by changing things to sine and cos, it might be like, ooh, I feel like I'm getting close. But on the left-hand side, I don't have a single fraction yet. I have a fraction multiplied by a fraction. Well, how do you multiply fractions? You multiply the tops, you multiply the bottoms. It's going to be really easy here to see that this is cos y over sine y. And now your left side and your right side are identical. So we write our statement that the left side is equal to the right side. Q, E, D. And we're done. Very nice. One more together, and then you get to work on these. 13. Tan of u over sine of u equals 1 over cos. So we rewrite the question that we want to prove. We draw the line at the equal sign. And at this moment, we want to see if we can get things to be the same. When deciding what to change, we can use that strategy I introduced in the last one. If there's a way to change things all to sine and cos, we'll see what happens. Well, what would I need to change? The only thing I need to change is the tan. If I change tan, it would be sine u over cos u. All divided by sine. And now our work from the beginning of class comes back. We need to have a single fraction. We have a fraction inside of a fraction. Here's my main dividing line. I'm going to make it thicker. How do you divide fractions? Because the bottom is a fraction as well. We can make it over 1. How do you divide fractions? You need to multiply by the reciprocal. So I rewrite this as sine u over cos u multiplied by the reciprocal 1 over sine u. Then how do you multiply fractions? Well, you multiply tops, multiply bottoms, but before I multiply it out, if you have a factor in common, and I hope you can see that there's a sine u on the top and a sine u on the bottom, that they simplify. And if those cancel out, and are left with 1s, then my answer on the top, 1 times 1 will be 1 over cos of u, which is exactly what we wanted. So we can write our statement. And we're done. So we've done 5, 9, and 13. You have the rest of the class. This is one of the units that you have to, like these identities, you have to practice and practice to see that where your fraction problems occur, and then you'll get good at it. So start with number 6. When you get stuck, call me over.